Assalamualaikum everyone. In today's lesson, we would be discussing shapes of orbitals and sigma and pi bond. Now, feel free to skip around the video. I'll put it in the description box when you could find shapes of orbitals and when you could find sigma and pi bond. So let's begin with shapes of orbitals. Now, in A levels, we basically learn about the S, the P, the D, and the F subshells. And we learn about this hierarchy that we first talk about a shell, which we also call as a principal quantum number, and then we move towards what we call as a subshell, and then we move towards what we call as the orbitals. So this is the hierarchy in which things work out, in which we define where an electron is basically placed. So first we talk about the shell, from there we move to the subshell, from the subshell we start discussing the orbital. So today we would basically be discussing the orbitals of S, P, D, F. If you have any confusion about how this hierarchy works or more details about them, you could search them up maybe, because in this lesson we are purely discussing about orbitals, and therefore I will assume that you know about these things beforehand. Okay, so let's begin. So first of all, the subshell that we will be discussing is the S subshell. Now the S subshell has only one orbital. Okay, that's something important to remember. It has only one type of orbital and only one orientation. Now S stands for spherical. So what you would see is something like this. This right here is 1s and this right here is 2s. Now let me define this, that orbitals are not 2D shapes. They in fact are these three-dimensional regions where the probability of finding an electron is maximum. And yet again we're talking about probability. We can't know for sure, and that is something that actually was derived from the uncertainty principle, which I find quite fascinating. So feel free to search the uncertainty principle on Google or maybe YouTube it, and you can find more on it. So we say orbitals are these 3D shapes, and the probability, we can't say for sure, but the probability of finding an electron within these shapes is maximum. Now S stands for spherical. Alright, so even though, because this screen is 2D, I have to draw it out like a circle, but this in fact is a spherical in terms of 3 dimension. Now 1s is closer to the nucleus, so imagining a nucleus right here, you can see that the boundaries of the 1s are much closer, or much they have a less distance from the nucleus. And this is 2s, and obviously because 2s is located in the second quantum shell, it has a greater distance from the nucleus. And if I were to draw, let's say, 3s, then it would have been even bigger than 2s. So as you move away from the nucleus, the shape of the spherical orbital gets bigger and bigger and bigger, but it stays a spherical, it stays a circle if you have to draw it in 2D. Okay, so this is what a S orbital looks like. So this is 1s and this is 2s. Let's talk about the P orbital. Now when we were discussing the P subshell, the scientists found out that there were 3 possible orientations. So about the P, right now we're discussing the P subshell. Scientists found out that there are 3 possible orientations here. And one orientation could be in the x-axis, one orientation could be in the y-axis, and one could be in the z-axis. So they decided to label these. Now, if I had this axis, which is basically a 3-dimensional axis, maybe I would write x over here, and I could write y over here, maybe z over here. You know, in the exam, if the examiner has not stated a specific dimension or a specific way to make the graph, feel free to maybe make y over here and z over here. It's up to you. So this is X and this is Y for me and Z. So X, Y, and Z. So now we can no longer discuss about the p orbital in 2D. We have to move to 3D because there are three orientations that we need to discuss. Now the p orbital looks like a dumbbell shaped, like an hourglass. I hope you guys have seen something like this. This is called an hourglass. So you see this sand coming down, and this is basically a way of measuring time. So it looks like an hourglass, it looks like a dumbbell. So let's first draw what I would call as a px, and then I'll draw the py, and lastly the pz. Now the px, as the name suggests, is it has an orientation along the x-axis. So you would draw something like that. And py is something that is a p orbital oriented along the y-axis, so something like this. And finally the pz is an orbital that is oriented around the z-axis, so something like that. Now again, this in itself is a 3D shape. It's a 3D shape. It's an hourglass shaped, a dumbbell shaped, a 3D shape. Mind that it's a 3D, it's not 2D. And again, the probability of finding an electron within this shape, within these things, is maximum. Okay, and let's say for example I'm discussing the 2p, the second shell, then I can write this down as 2px, 2py, 2pz. In this case, the 2 refers to what I'm denoting with n, basically the principal quantum shell or the principal quantum number. This right here is telling me about the orbital shape. Okay, and this right here is telling me about the orientation. I won't be discussing the D subshell in this lesson. I'll make a separate video on the D subshell. But for now, we're just discussing the the s orbital and the p orbital, and I'll make a separate video on the D one. Okay, so I hope this is clear. Now let's talk about sigma and pi bond. So there are a few important things to note over here. First, I will be discussing the sigma bond. Now, the sigma bond is denoted by a Greek letter. It's a Greek symbol, sorry. Right, this denotes sigma. And over here, I can discuss the pi bond, which all of us are familiar with. Pi looks like something like this. Again, it's a Greek letter. Now, the sigma bond is defined as the first bond, formed between two atoms. So the first bond formed between any two atoms is the sigma bond. Let's take an example. For example, CC. This is the first bond formed between two carbon atoms, so it will be a sigma bond. For example, CH. That's a sigma bond as well. For example, HCl. All of these are examples of sigma bonds. So wherever, in other words, you see a single bond, okay, wherever you see a single bond, know that it's a sigma bond. Now, touching a little bit on hybridization, which I will be discussing in a separate video, sigma bonds can be formed by hybridized or unhybridized orbitals. Now, when do we have either of these cases? We will discuss that when we get to hybridization, but for now, know that sigma bond can be formed between hybridized or unhybridized orbitals, both. And we will learn the examples and we will go through it and understand when it's either of these cases. Talking about the pi bond, it's basically any second or third bond formed between two atoms. So in this case, let's talk about how about C double C bond and C triple C bond. Now in this case, one of these is, the first bond, whichever bond it was, the first bond that was formed was sigma, but the second one was pi. And in this case, the first bond, whichever one again it was a sigma bond, but the remaining two that were formed were two pi bonds. Okay, and please note over here that pi bond is always formed between unhybridized p orbitals. So even though in the case of sigma you can have either hybridized or unhybridized orbitals, but in the case of pi it will always be unhybridized p orbitals. Now let's look at some examples. So this is methane, it's an alkane, and so you can see that carbon over here is making a single bond with hydrogen, and a single bond with this hydrogen, and a single bond with this hydrogen, and a single bond with this hydrogen. So we technically have 4 signal bonds involved, which makes it equal to 4 sigma bonds. So single bonds, sigma bonds. Let's look at another example. This is ethene, it's an alkene. In this case, you could say that this is the first bond between one carbon and the other. This is one single bond between one carbon and hydrogen, and then another one, and then another one, and then another one. And all together I see 1, 2, 3, 4, 5 sigma bonds. However, what about this one? Isn't this a second bond that is being formed between two carbon atoms? Yes, it is. Because carbon and carbon, these are two different atoms, and they have a single bond made between them, and then they had another bond made between them, and therefore it was the second bond, and the second bond is the pi bond. So we also have one pi bond here. Okay, so in this case we have ethyne, which is an alkane. An alkyne. And now let's look over here. So carbon and hydrogen have a single bond and a single bond. So that's actually a sigma and a sigma. And then these two carbons have one single bond, which is again a sigma, but they have two more bonds formed between them. So they have a second bond and a third bond as well. And a second and a third bond is always a pi bond. So we have two pi bonds as well. So in conclusion, what we have is 3 sigma bonds and 2 pi bonds. So I hope now you can actually look for the sigma and the pi bonds between atoms, and we will go to some more complicated examples later on. But in the second part of this video, we'll discuss more specifically about the properties of the sigma and pi bond, and that will make these things even more clear and more, you could say, it will provide you more information on what a sigma and pi bond is and how it really affects a molecule. So I hope this introduction to shapes of orbitals and to sigma and pi bonds was helpful. So till next class, Khuda Hafiz.